Hello, AP Calculus students. It's Mr. Ford here in the home studio once again. Hopefully your summer's going really well. Today we're looking at topic O, solving inequalities. And before we start, really only have a couple things to say about inequalities versus equations. So let's just think about this for a minute, maybe off to the side here. Inequalities versus equations. So an equation is anything that compares two quantities, like A and B, with an equal sign, saying that they are the same as each other. But of course, there are kind of, if you want to think about it, maybe even metaphysically, there are three states that A and B can be in. A can be less than B, A could be equal to B, or A could be greater than B. So the other cases, we could have A and B. We could have it be the case that A is greater than B, or that A is less than B. Of course, there is also the additional cases where A and B have this less than or equal to relationship or greater than or equal to relationship that we're talking about there. Of course, just remember the old trick that the alligator's mouth eats the bigger quantity, and that's what we're saying here. Now, the good news is if we're solving equations, usually the way we think about this is if you got a teeter-totter and it is in perfect balance, A and B are both the same, if you subtract 5 over here or subtract 5 over here, they're still going to be the same. The cool thing about this principle is that it still works if you have the teeter-totter out of balance also. If A is, for example, less than B, and you subtract 5 from both sides, A is still less than B. And the same thing is true the other way too. So we can use pretty much all of the exact same strategies to solve these problems that we would use to solve regular equations. There might be one last thing we got to remember, and if we do, we'll talk about it later on. So let's just jump right into it. So question number 1, all we're going to do here is solve this the way we would normally. We'll distribute the 5, get 5x minus 15, less than or equal to 8x plus 40. Distribute the 8 as well. So distribute the 5, distribute the 8. From here it's a really straightforward, maybe like a algebra 1, maybe a middle school math level of problem. I never really know the curriculum that well. I do, as I'm working through this problem without really narrating what I'm doing, I think it's a good idea as you go through the class to make sure you show all your work on everything. And I don't know at what point in a student's career that becomes a thing that you avoid. Like, oh, I don't need to show my work. I do it all in my head. Yeah, but you really don't want to because you want to be able to see the progression. And the further you study mathematics and science applications especially, it's more important to look at how you arrived at the destination than the destination itself. So that's my preachy bit here. 55 divided by 3. I don't have a calculator, but I suspect that 55 does not divide evenly by 3. Let me use the old phone calculator. No, don't ignore TikTok. Let's see, 3. That's not. So, honestly, I'm just going to leave it as that. Negative 55 and a third. Or sorry, negative 55 over 3 is less than or equal to x. Might be the way that you say that answer. That's the idea. So x has to be, you could say x is greater than or equal to negative 55 over 3, or x is less than or equal to. For maybe a number reference, my calculator says that is negative 18 and 1/3, if you really want a number reference there. That's that. You could, of course, test this, which is nice about testing it is just pick any number that's greater than negative 18.3. How about 0, for example? 0 is bigger, and so it should give us a true statement here. 0 minus 3 is negative 3. This would give us negative 15, less than or equal to 8 times 5, which is 40, and that is, in fact, true. Negative 15 is less than or equal to 40, so we're good. Let's try another one. These are going to get a little harder, I think, pretty quick, so let's try here. Now, the first thing we got here is this negative sign there, and I think that negative sign distributes the way it would normally to anything else. And 5 minus 4x over 3 is greater than negative 2x minus 1/2. It's a good idea, I think, at the start of this problem to just multiply everything by 6. We saw that strategy in a previous problem. If you multiply everything by 6, it'll cancel out all of the fractions. And the greater than sign will be unaffected. You'll have 24 minus 6 divided by 3 is 2, and 2 times 5 is 10x, greater than negative 12x minus 3, like that. And now this problem's a lot easier to deal with. It is to your interest to keep your coefficients positive, especially in these kind of problems. So I'm going to add that 12x over and get 24 plus 2x greater than negative 3. Subtract the 24 over. Get 2x is greater than negative 27, and x is greater than whatever negative 27 over 2 is. I like this as an answer, but that's going to be 13.5. Yeah, that works too. Whatever you want to do. Now, according to my... Oh, it's a typo. So I'm looking at the... I always have my eyes on the answer guide that came with this thing. Although I didn't publish it because it's full of mistakes. I'm just making sure. So it's negative 27 over 2. That works. It is helpful to look at somebody else's work. Okay, now we got the famous dual inequality. This is the mathematician's way of describing the word between. X plus 1 has to be between 3/4 and 1/2 is what we're saying here. Now the good news is we can solve this pretty much like any other math problem we would. Let's just subtract 1 from, well, in this case, all 3 sides. So in order to get that 1 by itself, or get that x by itself, we're going to subtract 1 from it. 1 minus 1 is 0. Of course, I'm going to edit this a little bit, because subtracting 1 is kind of weird. How about we subtract 4/4? And, subtracting 1, why don't we subtract 2 halves? See, it's always a good idea when you're dealing with fractions, especially adding and subtracting fractions, to just go ahead and convert it to a fraction with the same denominator whenever possible. So this is how I know 3/4 minus 4/4 is negative 1/4, which is greater than x. And then 1/2 minus 2/2 is negative 1/2. And there you go. X has to be, looks like less than negative 1/4, but also greater than negative 1/2, which does make sense. It's a little bit backwards. I would often see this one written as negative 1/2 less than x less than negative 1/4, but that's the same answer, just flipped around. Question number 4. Okay, here we go. Now we get to the absolute value inequalities, and here's where we might need to think a little bit about what's going on here. Let's say that we had 5 is greater than or equal to the absolute value of x. Let's just think about answers to that question for a minute. What values of x would work to make that true, considering that the absolute value will make whatever's inside of it positive no matter what? Well, if you have any number that's greater than 5, greater than or equal to 5, that won't work. Greater than 5, because it could be. So, like 5.1 doesn't work. 10 doesn't work. 100 doesn't work. But also, if we go into the negative territory, negative 5.1 doesn't work. Negative 10 and negative 100, they don't work either, because the absolute value makes them positive. So what we're looking for here is we got kind of 2 sets of numbers that we're dealing with. We're looking for numbers that are less than or equal to 5, which is kind of what the original equation just says. Sorry, inequality says. But we also need to think about numbers that are greater than or equal to negative 5. I think that's the key here. You want to split this up into 2 inequalities, and I think that's the best way to handle this problem. So keep in mind, though, we will possibly run into a situation where we get an answer that doesn't make any mathematical sense, so we'll need to check our work along the way. But let's try to take this simpler example and apply it to what we're dealing with right now. So let's start by taking the original inside of the absolute value, 5 minus 3x. Just like the previous lesson, we will not touch that negative sign. I'm going to write it down twice. 5 minus 3x, 5 minus 3x. Now, the first one I'm going to write is going to follow exactly what this says. I am going to flip that greater than equal to sign down to a less than or equal because I've switched the sides. But I'm saying that 5 minus 3x is less than or equal to the original x plus 7. But we also need to consider the fact that it could be greater than or equal to negative, in parentheses, x plus 7. So we're taking the same lesson that we learned by doing that example there off to the side, right over here. We're kind of applying it to a broader scope. If you want to follow the pattern, here's the way I'm thinking about it. The inside of the absolute value is the x. We've done that twice. That stays exactly the same. The first one is less than or equal to, which matches what the original problem said, along with its original positive version. And this one has the flip. This one's got the reverse, but now it's negative, like that. So from here, we're going to solve it. Once you get it set up, it's pretty elementary, I think. Over here, we'll have negative 3x less than or equal to x plus 2. Now, we are going to have to use a bit of a trick here because we're going to subtract x from both sides to solve this, and we'll get negative 4x less than or equal to 2. Now, here's what we're going to do here is we're going to divide by negative 4, and we have to be aware of what we're doing here because when you divide or multiply an inequality by a negative number, what you're going to do is you're going to kind of flip the agreement. You're doing pretty much the same thing we did when I took the original problem and wrote it backwards. We're doing that same thing because we're multiplying by negatives. So all the negatives become positive, all the positives become negatives. So the greater than, or sorry, the less than or equal to sign that I'm using there right here has to flip. So this is going to become x is greater than or equal to negative 1/2. And that will be the first part of our problem, first answer section. We'll have to test that in a minute because this does have the potential to create extraneous solutions. The other problem, though, we got 5 minus 3x is greater than or equal to negative x minus 7. We're going to handle this problem pretty much the same way. We will not run into that situation we had before because we'll have a positive 2x on that right side. 2x minus 7. We'll add that 7 over. 12 is greater than or equal to 2x. So 6 is greater than or equal to x. So we're dealing with a situation where we're looking for numbers that are less than or equal to 6, but also greater than or equal to negative 1/2. That appears to be the range of numbers that we're dealing with. You know, a good tester in that case is 0, again, because 0 is in that set of numbers. 5 minus nothing is 5, and 0 plus 7. 7 is greater than or equal to 5, so it totally works. So I think that our answer here is, if I'm reading these correctly, yeah, there you go. Pretty cool. Okay, let's see how hard these get. Question number 5. We got a quadratic equation this time. Now we have to remember that in this case, when we take the square root of this, what you need to remember is that when you square something, it's kind of like the absolute value with an added mathematical implication. Squaring something always makes it positive. So we need to think of numbers that, well, here's a really good way to think about this question. This number here would have to be either 5 or negative 5, because those two numbers are the numbers when you square it give you a number that's 25. So we might think about this kind of like the previous problem. Yeah, let's think about that. Like if we had x squared is less than 25, well, that would mean that x would have to be less than 5, or x would have to be greater than negative 5. If I'm really thinking about that correctly, because that's kind of the thing that's happening here. 4 squared, for example, is 16, and that's less than 25, and negative 4 is also 16, negative 4 squared, that is. So, but as soon as you go outside of the range of 5 to negative 5, you're out. So what we should consider here is, let's just replace this x in this kind of simpler example with an x plus 2. That'll make the problem really easy. What we know is that x plus 2 has to be less than 5, or x plus 2 has to be greater than negative 5. And these are easy to solve. X should be less than 3, or x should be greater than negative 7. Basically, any number in that set will do the trick. We could put those two facts together. X must be between 3 and negative 7, if you put them all together like that. So again, you could test any number in that set. 0, again, is a convenient case. 0 plus 2 is 2. 2 squared is 4. 4 is less than 25. So totally works. Pretty cool. Let's try an exponential situation here. X to the third power less than 4x squared. Now we're going to approach this problem kind of the same way that we approached sorry, I lost my train of thought there, because I was thinking about, if we had graphing calculators, if we were allowed to use graphing calculators, this problem would be trivial, because you would just graph x to the third and then 4x squared and figure out when the x to the third graph is below the 4x squared graph. But we don't have that ability here because this is a no calculator operation. That's often the case in this class that we're dealing with, that you guys are taking in the fall. So we're going to tackle this problem very similar to how we tackled some of those quadratic and exponential equations up in a previous topic. Let's start by subtracting 4x squared from both sides. X to the third minus 4x squared must be less than 0. Now we're going to treat it a lot like one of those problems where two things multiplied together equals 0. It's less than 0, but the game is still kind of the same. You can factor an x squared out now, and that leaves x minus 4, which is less than 0. And so once again, we're really just identifying the places where this thing is equal to 0, or sorry, less than 0. Now I think what's important about this is that, well, let's just consider the equation that we've got right here. Actually, instead of thinking about it maybe in a more instead of thinking about it like an equation to solve, let's just think rationally about this. We have two things multiplied together, and we need them to be less than 0. In other words, negative. Less than 0 means negative. Now this piece over here is always positive. Because x squared, no matter what you plug in there, when you square it, it becomes a positive number. So that means that in order for this to be true, in order to have a negative number, we need x minus 4 to be less than 0. So basically, by explaining this piece over here, we can just kind of ignore x squared for a minute, because x squared is always positive, and we need a negative answer. So what do you multiply a positive number by to get a negative answer? Well, you need a negative number. So this becomes the problem x minus 4 is less than 0. Because we need that to be less than 0. And that happens when x is less than 4. And that would appear to be the answer that we're looking for. Again, you could test a couple numbers. 0, again, a convenient case. Is 0, let's see. Well, see, I don't like this answer totally, because 0 doesn't totally work. 0 is not less than itself. I think 0 is, again, I'm not going to graph this, but I think 0 is probably not in the domain of this answer. I think any other number would work. Let's just try 2, for example. 2 to the third power is less than 4 times 2 squared. Is that true? 2 to the third is 8. Let's see, 2 times 2 is 4, and 4 times 4 is 16, so that totally works. Let's see, that works. Negative numbers, I think, would always work, because any negative number to the third power is negative, but 4x squared will be positive. I think we just have to say that x can't be 0. We should, if we add that, x less than 4. If we wanted to do it in set notation, or sorry, interval notation, we'd go negative infinity to 0, and union that with 0 to 4. But basically the answer here is numbers that are less than 4, but not 0. 0 will not work. 0 creates a situation where they're equal to each other, not that. So I guess that comes out of this part of the answer anyway, doesn't it? So if this was a less than or equal to sign up here, then we'd be golden. We'd be fine. It would be all numbers, but the less than sign makes the 0 not work. Okay, that's enough rambling about that problem. Let's take a look at number 7. Okay, here's where things are going to start getting real. We're going to start applying a lot of the same stuff that we did in previous problems here. We're going to solve this exactly the same way we solved a lot of the problems up in, I forget which topic it was. It was a couple days ago I recorded it, but we're going to deal with these fractions by basically by multiplying everything by the least common multiple here. It might be a good idea to first get everything off on the left side and then leave 0 over on the one side, which is always a good idea when solving any sort of problem. Set it equal to 0 if you can. So we have 5 over x minus 6. That 5 looks too much like a 6. There we go. We're going to subtract 1 over x plus 2 from both sides and make it greater than or equal to 0. So this is a good common strategy that we use a lot in solving problems, is make them equal to 0 or less than or greater than or equal to 0. It makes it easy, because now if you can make this into a multiplication problem, you can really easily section off the parts that you're concerned with. Now we want to combine these two ideas together. We want to actually subtract these two fractions, so we need to give them a common denominator. So let's do that next. Let's start with 5 over x minus 6. This is going to get multiplied by x plus 2 over x plus 2, just like we did in a previous lesson. We're going to subtract from that. We have 1 over x plus 2. That's going to get multiplied by x minus 6 over x minus 6. And this is all greater than or equal to 0. And it will all make sense in a minute, I promise. Let's actually do the math now. On the top of the left term, we're going to have 5x plus 10 over our common multiple of x minus 6 times x plus 2. We have to be careful here. We are going to be subtracting a quantity. So we're going to subtract the quantity x minus 6. And that will also be over our common multiple, which I am going to change the order of on the bottom just to make sure it works. And now let's actually combine these ideas together before we think about our answer for a moment. So 5x plus 10 minus x minus 6, that's going to become 4x plus 16 over x minus 6 times x plus 2. And we want to know this when this is greater than or equal to 0. So what we're going to do in this to solve this problem, there's really nothing more we can do algebraically. At this point, we've hit kind of the end of our rope as far as what we can do solving this. Now, if we wanted to know when this equals 0, we would simply look at the top. We would solve when does 4x plus 16 equal 0, because in order to get 0 out of this equation, you need the top to be 0. If the bottom is 0, there's no solution. But we want to know when this will yield a positive number. So we really need to think about all of the pieces going on in this. There are three main players. There's 4x plus 16. There's x minus 6. I wanted it to be green. Come on, hang on. And then there's x plus 2. There are three main players. This is a very common thing we do in calculus, but it'll be brand new to you right now in this video. But what we're going to do is we're going to make what's called a sign chart. And to sign chart basically acknowledges the fact that there are basically three pieces. You have a thing divided by two things multiplied together. Now we are looking for the right combination of things that will give us a positive answer. That's going to happen if the top is positive and the bottom is positive, or if the top is negative and the bottom is negative. So we need to consider what's going to happen basically whenever these things, we need to figure out when these things are 0 and then kind of think about what's going to happen in our fraction. So we're going to make kind of a number line. And with our number line, we're going to think about our answer here, and we're going to consider where these things are 0. So start with the top, 4x plus 16. This is 0 if x is equal to negative 4. On the bottom, x minus 6 is 0 if x equals 6, and x plus 2 is 0 if x equals negative 2. So these are kind of our 3 points that we're going to think about on our number line. We're going to just section them off. They don't even need to be well spaced out. Negative 4, negative 2, and 6, like this. Now basically, as soon as you hop over one of these 3 borders, you're going to change the agreement in the problem. The agreements, the 3 things will, one of them or more of them will change from positive to negative. So let's start with the leftmost section. Let's think about numbers that are less than negative 4. Right over here. Let's start over here. Section 1. And all we're going to do here is play the game of if I plugged in a number that's less than negative 4, would I get a positive or a negative in all 3 of those chunks? So plugging in a negative into 4x minus 4x plus 16, negative 5, for example, would give us a negative number. So let's put a negative on top of a fraction like that. And plugging in, say, again, I'll use negative 5 as my example here. Negative 5 minus 6 is negative, and negative 5 plus 2 is also negative. So we'd have negative times negative. And so I think that's negative divided by positive, which would give us a negative answer. So this, I'm going to put my final answer underneath the sign chart. This would be a negative chunk of the problem. We're going to do that for all of the chunks. Let's try negative 3 as our next tester. So plugging in negative 3 would leave a positive number on top. But negative 3 minus 6 is still negative, and negative 3 plus 2 is also still negative. So now we have a positive divided by a positive, and that is going to give us a positive number. So this range of numbers will work to solve our original problem. Let's try negative 2 to 6. Fortunately, this one includes 0, which is usually the best one to include. So if we plug in 0, for example, the top becomes top stays positive. 0 minus 6, still negative, but 0 plus 2 is now positive. So what we get now is a positive number divided by a negative number, which is negative. And let's try a number that's greater than 6. Let's try, I don't know, 10, for example. 40 plus 16, definitely positive. On the bottom, 10 minus 6, positive, and 10 plus 2, all positive. Everything's positive here, so the answer will be positive. So that's our second range of numbers. So our final answer here, we're looking for kind of 2 sets of numbers. We're looking for values of x that are between greater than or equal to negative 4 and less than or equal to negative 2. And then also numbers that are greater than or equal to 6. Oh, you know what? We should not include the greater than or equal to's. The reason why, actually, no, hang on. We have to change. This is me being my super math nerdiest. We need to change a couple of these 2. So negative 4 is not a problem because negative 4 makes the top of the problem 0. And 0 is greater than or equal to 0. So we are not going to change that one. X could be greater than or equal to negative 4. However, it cannot be equal to 2 because if x is equal to, negative 2. If x is equal to negative 2, the bottom of the fraction becomes 0, and that causes the thing to be undefined. So it's got to be less than 2, if I'm being very super specific. The same thing is true about 6. X cannot be equal to 6 because that causes the bottom to be 0, so it's got to be greater than 6. That is the bestest answer I can offer you for this problem. Wow. That got away from me. And then let's try number 8, which only asks us to find the domain, which is a cool way to think, a cool way to end this exercise there. So finding the domain, consider the fact this doesn't seem like it fits in this set of problems, but it absolutely does, because look at what you got on the big thing there. You got a big square root, and square roots must be greater than or equal to 0. So really we're solving this problem. When is x squared minus x minus 6 over x minus 4? When is this greater than or equal to 0? This is the same kind of problem. So we're going to solve this exactly the same way we solved the last problem. We're going to factor that top, which I believe is x minus 3 times x plus 2. Just staring at it for a minute. And we're going to play the same game that we played in the last problem. We're going to make a little sign chart. Maybe I'll make this one a little bigger, having learned lessons from the previous one. This time our 3 key points are x equals 3, x equals negative 2, and x equals 4. Remember, it's kind of the opposite of what's going on inside of the quantity. So let's go ahead and put those numbers down on our chart here. Negative 2, 3, and 4. Remember, it doesn't have to be evenly spaced out. We're just looking for something to map out our thoughts onto. So again, let's plug some numbers in and see what happens. We're looking for numbers that are going to give us a positive answer here. So we should note right away that x cannot be equal to 4. That's a thing we should note right away. But okay, so let's try a number like negative 3, for example. Over here for the first range there, negative 3 would give us a negative on top again, and then negative 3 minus 4 is still negative, so this would be a positive answer. This is a winner over here. Plugging in a number between negative 2 and 3, let's try 0. That's always the nice one. 0 minus 3 is negative. 0 plus 2 is positive this time. 0 minus 4 still negative. So now you've got a negative divided by negative, which is... Oh, sorry, I misspoke a minute ago. Oh, that's not a winner, sorry. Over here you get a positive on top. Negative times negative is positive. Positive divided by negative is negative, so sorry, that doesn't work. And here you get a winner, because negative times positive on top here gives you positive. Negative. Oh, geez. And negative divided by negative is positive, so this is a winner down here. Between 3 and 4, that can be tricky to judge. I mean, you know, it might be a better idea to just recognize that, okay, at this point, x plus 2 is not going to change. We've already hopped over that border, so that's still going to be positive. On the bottom of the fraction, that's also not going to change. We haven't hit that border yet, so any number between 3 and 4 minus 4 is still negative. But now x minus 3 has now become positive. So it might just be beneficial to just keep in track which ones are going to change. This one is positive times positive is positive, divided by negative, which is negative. So not what we're looking for. And then the final section should work, because now the 4 will change. The bottom will change to positive. This is where everything becomes positive. And that is also positive. So I like this because it introduces kind of a way of problem solving that isn't so much just do these steps and circle the answer, man. It actually forces you to stop and think, okay, what numbers am I looking for? It's like a puzzle, and I really like that. So now our final answer. We know that x has to be between 3 and negative 2, and we can use the equal signs on there because those numbers will just produce 0 on the top. If you plug in negative 2 or positive 3, you'll get 0 on the top. It's 0. 0 is in the domain. That's fine. However, with 4, we cannot have 4 be a part of the problem because that will cause a 0 on the bottom. So x must be greater than 4, but not equal to it. There you go. Hey, that was a fun one. I really like that lesson. Just introducing you to, I mean, I hope by watching these you're starting to get just keep those juices flowing. This is a lot more traditional than what we're going to do in class this year. We are going to follow the CPM curriculum, which I really enjoy. It's a lot of explorations. Just keeping everything idea fresh, and really just teaching you to be an open-minded mathematician, because the problem with math students is they tend to be the kind of people that just want to know what the steps are. And that's not always the case. We want to introduce ideas and ways of thinking that explain why the formulas we're teaching you work. That's important. Anyway, you guys are awesome for making it through this video, for doing this work over the summertime. Really proud of you. Can't wait to work with you in class. You guys are going to be great. So don't forget, you're awesome. Go outside, enjoy yourself. I'll see you in the next video.